So in the previous video, we saw that the derivative of a function, of a parametrically defined function or a vector function, is gives us a vector which is tangent to the curve at a specific point, and we know that the direction of that vector is the direction of that vector is the direction of the tangent line. The question we ended with, though, is what is the length of that vector? Here was the example we had. We had f of t is equal to 3 cosine t plus 4 sine t. 3 cosine t in the I direction, and then 4 sine t in the j direction. And then the derivative was negative 3 sine t in the I direction and 4 cosine t in the j direction. And we found out that this vector right here, which we translated out to the end, is the tangent vector. But the question is, what does the length of it represent? Okay, well, not surprisingly, there's a reason why we use the letter t here, and the reason we use the letter t here is because it's helpful to think of t as time. And if I imagine I'm a little person, I'm a little guy. I'm a little guy who starts here near the curve, and as time goes on, I'm sort of walking around the curve, right? Okay, so this function tells me the position of the person at time t. Okay, so I have my person at time t, and here he is. So if I take the derivative of that, if I take the change in position, if we call it position p, so if I do df or dp dt, that's just going to be my velocity. That's telling you how fast he's changing. Okay, so that sort of makes sense because we know, if you know from physics class, hopefully you do, that a velocity is a vector, which means it has a direction and it has a magnitude. And we already know the direction. The direction is tangent to the curve, and that sort of makes sense because at any particular time, you can imagine that you're walking along at you imagine you're walking in a straight line, and then you just turn slightly, an instant later. So the length of this vector here represents the velocity, or this vector here represents the velocity. So what is the magnitude of that? The magnitude is the speed. So we know that f prime of t is velocity, and that means that the magnitude of f prime is speed. That's just telling you how fast you're going around the curve. Velocity is also telling you how fast you're going the curve, but it also includes that direction component to it. Okay, so this brings us to a pretty natural conclusion. Since we know that distance is equal to rate times time, if we know our speed is f prime of t, the magnitude of that, and then our time, times t, but maybe we want to think about this like an integral, so we're going to multiply by a small amount of time, and then if we integrate that, oops, that was a pretty ugly integral sign. If we integrate that from, say, t1 to t2, then we just have our distance. Okay. Now this equation right here that we've just written is true. Okay, the distance traveled by a particle moving with a speed which is defined by this little guy here between time 1 and time 2 is going to be given by this integral. So that distance is true. The problem is that this distance isn't always equal to arc length. You might think that, okay, so if I have some curve, here. If I want to know the distance traveled between this point and this point, right, I just want to, integrate my speed. The problem is, what happens if I don't walk nice and smooth? What happens if my little man, what happens if he, walks a little bit, then he says, oh wait, I forgot my wallet, so he goes back, and then he goes again, and he goes again. So his distance traveled there is not equal to this arc length, and the reason is because he backtracked. Okay, so we have to be a little bit careful. This equation is true. Distance is equal to the integral from time 1 to time 2 of the speed integrated with respect to dt. We don't need a dot product there. Those aren't vectors. That's just a multiplication the problem is arc length is not always equal to this. Arc length is only equal to this. Arc length equals distance only if you don't backtrack. And your textbook calls those things well-behaved functions. Okay, so I just wanted to drive this point home a little bit because it is sort of important by showing you a couple of examples. Okay, so here we have a unit circle, and unit circle, and we know the equation of a unit circle. But what I would like to do is I would like to discuss how we go around this in the how we can go around this. Now, the standard way of defining the unit circle parametrically would be something like f of t is equal to cosine of t I plus sine of t j. All right, and that'll get us going around, and we know that f prime of t is negative sine of t I plus cosine of t j, and we know that f prime of t is equal to sine squared plus cosine squared, and that's equal to 1, or the square root of that, but that's still equal to 1. So we have a nice constant speed. And if I put a point on this, okay, so if I put a point on here, and, sorry, if I put a point on here and let it go around, you can watch how I'm changing my parameter t. It's changing it nice and smooth, and the point is going around the curve nice and smooth. Okay, so let's watch that one more time just so we can see what's going on. This line right here is my parameter t. So this is telling me how I'm changing t. So I'm changing t nice and smoothly, and as I change t nice and smoothly, the point P goes around the curve also nice and smoothly. Great. Okay, so that's all well and good, but the problem is that we don't always define our unit circles that way. So let's take a different definition of the unit circle. What if instead of defining it the way I originally had, what if I defined it this way? Cosine of t cubed minus 3t squared plus 3t I plus sine of t cubed minus 3t squared plus 3t j. Okay, now this is much more complicated, but you can see that this is still going to give us the unit circle. And it's still going to give us the unit circle because the magnitude of this vector, f, is always 1. It's a cosine of something plus sine of the same thing. So when I take cosine squared plus sine squared, I get 1, no matter what t is. Doesn't matter how complicated that argument is inside there. So this is still the unit circle. All right. But if I take the derivative of this is something much more complicated, right? So the magnitude of this is not going to be our 1 like it was for the first time we did the unit circle. So if I watch this one, if I have this one and I called this guy Ant, because I imagine him as a little ant walking around the circle, and it's Ant B because we're going to do another example, which was my first ant. But anyway, so if we take Ant B and I let him go around the circle. Now, again, watch the parameter here. The parameter is going to go nice and smooth, but the ant is not. So as the parameter goes nice and smooth, the ant goes up a little bit. Oh, wait, and then he pauses, and then he keeps going. All right, so in this particular case, he did that. Now, the reason he did that was because t, if we think about what t looks like, t graphically is just, if I graphed t versus, t cubed minus 3t squared plus 3t, it actually looks like that. So you could almost see that as the point goes around, it sort of it goes pretty fast at the beginning, and then it sort of slowed down and stopped for a second, and then it sort of sped up again. So let's watch it again and see if we can't match what's happening to t with how it goes around the unit circle. So here's that, and I'm going to animate it again. So it goes up, it sort of slows down and stops, and then it starts to pick up speed again and goes, faster and faster and faster. Okay, so that's one way to do it. The problem, that one, not so much of a problem. If we did that, if we figured out the distance traveled, we'd still probably get the arc length. And that's because he doesn't backtrack. He may go at different speeds, but if we figured out the total time it took and integrated that, we should still get the arc length. But we can have even more complicated situations. And let's try one more here. Instead of defining our unit circle like that, we're going to find our unit circle as f of t is equal to cosine of t squared minus 2t, and I plus sine of t squared minus 2t. I should have moved that down on the second line. I'm going to do that. Sine of t squared minus 2t. Okay, again, because it's a sine term plus a cosine term, then we know that the magnitude of that is always going to be 1, so we're still going to have our unit circle. What happens now as the point goes around? Well, let's think about it a little bit ahead of time and see if we can't predict. So we have t squared minus 2t, so here's t, and then I'm going to graph t squared minus 2t. The starts off at 0. We have a 0 intercept, and we also have, if you factor this as t times t minus 2, our second 0 is at 2, and it sort of goes like this, right? It's a parabola. Okay, so what we'd imagine is that as our point starts here, it's going to start by moving backward, actually in the wrong direction. It's going to stop for a second, turn around, come back towards where it started, and then go around the circle. So let's see if that's actually what's going to happen. Okay, here it goes. Oh, it's backtracking, slows down, stops, turns around, heads back to where it started, and then it continues around the circle. Okay, so in this particular case, if we just integrated this function, if we just integrated the distance, if we just did the integral of the speed, right, we would not get the arc length. And that's because it backtracks. Good. Now, the textbook does a fine job of explaining to you how to calculate the arc length if you understand the fact that this is happening in the right direction. So make sure you read carefully the textbook so you understand how to solve these types of problems. But the point of this video was to explore what happens if the functions aren't behaved nicely, just like the textbook warns.